technology in Barcelona, Spain. And she have a lot of academia and industry exposures on quantum information and quantum technologies. She obtained her PhD in physics from University of York, and her master's degree on theoretical chemistry and computational modeling from University of Illes Bear. Sorry for wrong pronunciations. So with that brief introduction, without taking much time, I would invite Dr. Marta to the stage and share her thoughts about the quantum technology in this workshop.
Thank you very much. Can you hear me well?
Yes. Yes.
Okay, perfect. I'll try to share my screen now. Can you see my screen, like the full presentation?
Yes, but the screen size is a little small. Probably it needs.
Oh, so you see the presenter view, maybe.
Yeah, so you could duplicate it, probably then that will work. So
okay, I'll try to do something different. Is now better?
Yes.
Now you see it full.
Yeah, you can see the
okay. Okay. Okay, so thank you very much for the introduction, and also thank you very much for the invitation. I've seen that this summer school is huge. There's a lot of attendees, and I'm very excited about that, about so many people being interested in quantum technologies. I think this is a very good sign. And actually, one of the challenges that we face in quantum technologies is the lack of talent, the lack of researchers in the field. So the fact that there are so many students and so many people interested is very encouraging, because that might solve many of the challenges that we have at the moment. So I'm Marta Estarellass. I'm a senior quantum engineer and team lead of the theory team at Qilimanjaro Quantum Tech. And today I wanted to present more of not so technical presentation. I'm not going to talk so much about the insights of quantum technology or quantum computing, but I wanted to focus more on what we do in Qilimanjaro and what we do different from other companies. Qilimanjaro is a startup from Barcelona, Spain, and we've been there already for 3 years. And what we want to do is to develop coherent, and this word is very important, coherent analog quantum computers, and we want to bring them from the lab to the industry. We are a bunch of scientists that most of us come from academia, and it's a real challenge to do this step of going from the university research to the industry and bring solutions to real problems. So in that sense, we come from the Qilimanjaro was founded from 3 main institutions, scientific institutions in Barcelona. The first one is IFAE. This is the High Energy Physics Institute in Catalonia. The BSC, the Barcelona Supercomputing Center. This is a very large institution on high performance quantum computing, also in Barcelona, and the University of Barcelona, which is one of the main universities there in Catalonia. Okay, so how can I move slides? Okay, there we go. So this is the Qilimanjaro's founding team. As I said before, we have a variety of people that comes from academia, very well established in academia, and people that come from the business side. And that allows us to have this balance of knowledge on how to run a business and the knowledge on how to build quantum computers. Victor Canivel is our CBO. he's bringing most of the business perspective to the company, and how to interact with clients, with investors, and so on, and how to organize all the business side. He had a long track record in startups and also in big Silicon Valley companies, tech companies. Then we have Jose Ignacio Latorre. He's our Chief Science Officer, and he was one of the instigators of Qilimanjaro to be created. He's quite well known in the field. He's the director of the QIQT in Singapore, and he's also the director of TII, a new research center in quantum technologies that is being built in Abu Dhabi, in the Emirates. Then we have Paul Forn-Diaz. Paul Forn is our chief hardware architect. He's very well known for his work in the superconducting qubit technology. He's in charge of orchestrating all the efforts regarding the hardware. Then we have Artur García Saez. He's part of the BSc, the HPC center I mentioned before, and he's in charge of all the software part of the company. And finally, we have Jordi Blasco, the last founder. He's our Chief Financial and Legal Office, and he's helping us with all the legal matters and other things. Okay, so let's go into a broad overview of quantum computing today. As you know, since the early decades of the 20th century, quantum mechanics not only has allowed us to better understand nature, mainly what happens at the very microscopic scales, but has also had an important impact in many fields, such as medicine, such as biology, and so on. Computer science has not been an exception, and quantum computing then arises as a new way of doing computation based on the laws of quantum mechanics, as you all know. The qubits are the analogous to bits and are defined as the basic units of quantum information. And the power comes due to the fact that these qubits, these units, can be part of what are called superpositions and entangled states. These two key quantum features can be used to do computation in a much faster way and hopefully in a most efficient way. And this is precisely what makes quantum computers so interesting and very promising. We believe that the solution to many practical problems that you can encounter in logistics, in finance, I believe in the previous talk you were talking about problems in finance, cryptography, chemistry, material science, and a long list of examples, is limited by the computational capabilities of the current technology of the classical computers that we have. And the reason is that many of these problems are too big or too complex, that are out of reach due to the unreasonable amount of time or amount of memory that they require to be computed. This generally means that many approximations and assumptions need to be made to simplify these problems. Also, the semiconductor industry keeps trying to increase the power of the processors that we have, the classical processors, but there's a fundamental limit that has been reached, and this is what it's known as Moore's law. I'm sure you have all heard about this as well. And what this limit implies is that we cannot keep fitting more transistors into an integrated circuit at the same pace that we have been doing so far. This means that we cannot maintain the level of increase of the digital capabilities that we have all witnessed for the last 50 years, and that has been a crucial drive in the technological and social growth of the world. I mean, we have witnessed a true technological revolution thanks to the classical machines. But now we think that changing to a different computing paradigm, such as quantum computing, has the potential to lift those limitations and keep the pace in this technological revolution. We believe that this technology could provide means to accelerate all these heavy computing problems that I mentioned before, that we are limited in finding solutions. And then we wouldn't need to make all that many assumptions. And this would allow not only to provide faster results, but hopefully more accurate ones. So we would be dealing with exact solutions and not approximations coming from heuristics. We think that it is clear that the successful development of this technology would suppose a huge impact in the industry. Okay, but with such a promise, we are not the only ones that noticing this, and we see a rapidly growing excitement and development of the technology and its surroundings, not only in the quantum computing sense, but also in the quantum technologies in general. This includes quantum sensing, quantum communications, quantum cryptography, and so on. There's a lot of interest. And this makes us to be part of a very large ecosystem that is being formed in not only in academia, but also in industry. And I think an important motivator for this that encourages the community to push towards quantum computing and start investing in these companies happened in 2019. I have these two examples of these newspapers reviews. This was when Google published their quantum supremacy paper showing the first proof of a principal application of a superconducting based device that could outperform a classical task. This same experiment has more recently been replicated by two different teams in China, also with different hardware architectures. And more recently, we had been other quantum advantage experiments that have been done with in the context of boson sampling. Okay, so all of this triggered other players in the industry to put their focus on that, and also a lot of interest from potential clients that want to use this technology. And now we have a variety of prototypes available. As you know, we have a prototype from QIQT, we have prototypes from IBM, we have prototypes from D-Wave that we can access through the cloud. And these are called NISQ devices, noisy intermediate scale quantum devices. And most of them, while we have a variety of architectures in terms of hardware for those, most of them focus on the gate model of quantum computation. And I must say that while these are outstanding technological achievements, all these advantage experiments and so on, the application of these supremacy experiments is quite artificial. This means that they lack of practicality in the industry, and so far it does not provide what is more well known as quantum advantage or quantum practicality. So we understand there's a big debate on how we define quantum supremacy, quantum advantage, and so on. But my opinion, and what others also believe, is that quantum advantage is when you find an application, you find an advantage of using a quantum device over a classical machine that provides a real practical advantage for a real problem. And this doesn't have to be only in terms of time or memory. We are actually now considering different benchmarks to see where the quantum advantage could come from. And for instance, one that we are very interested in is energy consumption. So if we can find that quantum computers can solve the same problem as a classical computer, maybe not faster, maybe not consuming less memory, but with less energy consumption, that would be very important, because nowadays we are realizing how important is sustainability of the technology we are fabricating. Okay, so the conclusion of this lack of practical quantum advantage proof is that
Dr. Marta, sorry to interrupt.
Yes?
Are you moving your slide? Because we are in probably the second slide.
No, I'm still talking here. Sorry. Yeah, okay. I haven't moved the slide. Yeah, so I'm now moving. So the implementation for a more widespread or what is called also universal applications and the reach of quantum advantages is currently blocked by the need of this challenge that I mentioned here, which is the need for error correction. Qubits are very sensitive to the noise of the environment, as you know, and the information that is contained in this device gets quickly faulty, so it quickly acquires errors. And we cannot do anything with. We cannot make any sense out of this information anymore when the errors are too big. And error correction techniques can mitigate and correct for these errors, but at the expense of encoding this information into many redundant qubits. This basically means that we can encode logical degrees of freedom into many physical qubits. So we can have a logical qubit that is formed by many physical qubits. This is very similar to how error correction redundancy-based methods function in classical computers. But yeah, the challenge is that we need more qubits and we need more control. And that's a very high technological challenge in as I said, both in fabrication and control. And the technology, I must say, is not quite ready yet to overcome this challenge, and it's not expected to be ready for at least another decade, even though it's true that it advances very quickly. So we see technology overcoming big milestones faster than we expected. So I do have hopes to see large error correction codes being implemented. Okay, so in what about Qilimanjaro, how Qilimanjaro fits in this picture? So in the meantime, while we are developing all these error correction protocols and we are developing the technology such that we can fit more qubits and have a more precise control, Qilimanjaro is putting a focus not only in developing these NIST devices, this NIST technology, but also exploiting these devices to be used as dedicated and not universal, dedicated devices that give solution to only certain commercial applications. And this is with the aim to speed up the technology readiness. This is the time to market that the technology has, so when the technology can come to be being used by the market. Okay, so this is our main mission. So Qilimanjaro wants to bring practical applications of quantum computing in a shorter time frame than the general purpose gate-based ones that are currently being developed. And to achieve this, we propose a different way of building and using quantum computers based on what is known as the adiabatic model of quantum computation. This model differs very much from the more widespread and used gate-based model as follows. The first differentiation is the encoding. In the gate-based model, as you probably know, we encode the problem that we have in a sequence of gates. This is very similar in the logic is very similar to the way the logic works in classical computing. So we have a set of gates in our ALU, in our processor, in classical processor, that we keep applying, and that transforms our information to the state that we want. The difference here is that we are not using classical gates, we are using quantum gates that have a different behavior, totally different behavior than classical ones. Then the solution of the problem is revealed by the final state after all the application, all this sequential application of gates, and then we just have to measure. In the analog or adiabatic-based model, the problem that you want to solve is encoded in a Hamiltonian. As you probably know, the Hamiltonian is a mathematical construct that defines the dynamics of a quantum system. And this Hamiltonian can be associated to the tunable parameters. Well, you have enough tunable parameters in your chip, you can associate this Hamiltonian to these parameters of the quantum chip. And if the encoding is done in a smart way, this is very key, and this is kind of the magic of this model. The solution of the problem will be contained in the ground state. This is the state of minimum energy of the quantum system. And I will explain how this works with more detail in the next slide. Okay, another big difference is the control. The control of gate-based quantum computer is carried through the application of, as I said before, a set of discrete gates, and this gets translated into a set of discrete and fast pulses that are being sent with a lot of control into the qubits. This requires a lot of control, and you need to do it very fast. On the other side, I'm making reference to the word analog. The control in the quantum annealer, when I say quantum annealer, adiabatic-based quantum computer, or analog, I'm trying to talk about the same type of models. What we do with the analog is to do control by the continuous and slow modulation of the Hamiltonian parameters. And these Hamiltonian parameters, as I said before, should be mapped to the tunable parameters that you have in your chip device. So what you're doing, you can imagine that your system has a set of knobs, and you slowly turn these knobs to do the control of your Hamiltonian parameters. And then a very important difference is universality. The gate-based model has been proved to be universal. This means that in principle, it can perform any quantum algorithm. And for this, this model is often called general purpose model of quantum computation. As I said before, this comes with a cost. This comes with the need of error correction. And this is a requirement that I should really mention is not available yet. So we can have small devices under this model, but they have errors, and we cannot really do a large variety of algorithms with such a small circuits. Now, quantum adiabatic, quantum annealing, or quantum analog has the potential to be universal. So what do I mean by this? There's a theoretical proof that shows that quantum analog, quantum annealing is equivalent to the gate-based model. This means that you can, in principle, simulate any gate-based model, any gate-based circuit into the analog framework in a polynomial time. So this means that you can efficiently map one to another. Having said that, it's quite challenging to have the ability to encode any arbitrary problem into a Hamiltonian due to some technological limitations. I will talk about this later. So quantum analog is not free of limitations. We have several limitations, but some problems, mainly optimization tasks, and that's what I said before, that we wanted to focus this model for dedicated tasks, not general purpose. For some tasks, such as this optimization task, this model is very adequate. It works very well. And the reason is because there's a very easy mapping from the mathematical formulation of some of these optimization tasks into the formulation in Hamiltonian that can be embedded into the quantum device. And in principle, up to certain limits, this model could bypass the need of error correction, the need of having large redundancy of qubits to keep your computation free of errors, because it follows the Adiabatic theorem. And if you do things slowly and accurately enough, you should avoid the errors in a better way than sending very fast pulses. So the key is that fast pulses introduce a lot of errors, but slow continuous modulation can save you many of them. Okay, so I'm going to explain with a bit more detail how this model works. The general idea, and this has a lot of variants, but the general idea is that you can encode the problem into a Hamiltonian that we call HF. And this Hamiltonian is a construct that can be enforced through the, as I said before, through the tuning of the chip parameters. And this is the local fields of your qubits and the interaction strengths and the connectivity and so on. Having complete manipulation of those allows you to encode arbitrary Hamiltonians. Okay, and this means that every Hamiltonian corresponds to a different chip configuration. with a different set of parameters. And each Hamiltonian, as you know, has associated a set of possible states with different energies. These are the eigenstates of the Hamiltonian. And from these eigenstates, the ground state is the state with lowest energy. And the one that contains, if the encoding has been done in the right way, the one that contains a solution. So for instance, this is my final Hamiltonian, this is the energy, and I will be looking at the eigenstates. The lower one would be the ground state because it's the one with the lowest energy. Then we would have the first excited state, second excited state, and so on. Now, we want to reach this ground state because it has a solution, but it's not trivial to prepare the ground state. And it's not as easy as, okay, I'm going to prepare the Hamiltonian and then I'm going to measure. No, it's not that simple because it is very likely that you won't be in the ground state. You will be in a superposition of many of the eigenstates. So finding this state is in principle difficult, and for that that's the key of the annealing. For that, we start the computation in the ground state of a Hamiltonian that we know how to prepare. And this is what we call H0. This is the initial Hamiltonian that has a ground state that it's easy to prepare. For instance, this Hamiltonian is usually the sigma x Hamiltonian. So we prepare all the qubits in the sigma x. And sorry, the Hamiltonian has a sum overall qubits of sigma x, or the polymetries, sigma x. And then that means that the ground state is usually superposition of all the possible states, the plus state at each qubit. So we prepare each qubit at the plus state or the minus state. I don't exactly remember which one is it, but it's something that is very easy to prepare. And okay, what the Adiabatic Theorem says that if we interpolate between H0 and HF through the parameter S, and the parameter S is controlled by these tuning of parameters, if we do it slowly enough, and we go from here to here, we can guarantee that the system will remain in the ground state towards the entire computation. So basically, this is the idea. But for this, we need to guarantee that we do things slow enough. And this interpolation that is defined by this modulation of S is called also as a schedule. And it's as I said, it's governed by the modulation of the parameters of your chip. Okay, so then if the modulation of the parameters of your chip is done slow enough, you reach the ground state with a high probability, and then the only thing that you need to do is to measure, and that's the solution of your problem, and you're done. Okay, and after a bit of introduction to the idea behind the technology that we want to develop in Qilimanjaro, I would like to explain what is Qilimanjaro solution and how it differentiates from the rest of available proposals that we have. What we have is full stack quantum computing solution. This is our product that contains both hardware, classical software, and quantum software. So that's very ambitious because usually small startups as ours focus on one thing, either software, either hardware, or just one part of the hardware. We focus on everything. So we want to be able to control the full stack of the quantum technology framework, because we think that by having the ability to have very well integrated teams, we can co-develop better the device and the algorithms, and also how everything connects through all the classical software stack. So the end product is that we want to provide our clients with cloud access to both our quantum hardware, but also the simulators that we develop through a very easy to use interface, classical interface. And the idea is that from this interface and from this cloud access, they can run their own experiments and their own algorithms, but we can also provide them with tailored solution in terms of quantum algorithms that are adapted to their specific use cases, because that's something that we see very often. So we see companies in finance, companies in logistics that really want to try quantum computing. They have their problems, classical problems, and they know them very well, and they have algorithms that work very well. But they say, "Hey, I wanna see how I could how could I solve this problem in a quantum computer?" It usually has to be simplification of the problems, because as I said, quantum computing is still only capable to handle small problems. But this mapping from the classical problem that they have, the use case, to the quantum algorithm is something that they generally don't know how to do. And this is something that we provide them. We sit down with them, we understand their problem, we understand their algorithm, and we find the quantum counterpart. And we do all this process of mapping the classical algorithm to the quantum algorithm. So we also have provided this service to the client. Okay, so we have this full stack solution, and now let's look into each of these parts of the solution. Our hardware infrastructure is very much defined by this coherent quantum annealer or coherent analog quantum computer. And I must say, this is not the only type of quantum hardware that we develop. We also have a lab where we develop gate-based chips, but this is the one that differentiates us most, because this is the one that is based on the computational paradigm that I explained before. So this chip is fully designed to run algorithms under this analog model of quantum computation that I explained. And this is built out of superconducting flux qubit technology. This is very important. We are using flux qubits. For gate-based, you generally use transmon qubits. We have both. We have technology. We are developing transmon qubit devices, and we develop flux qubit devices. So we think that our approach to this flux qubit device has important improvements to overcome some of the limitations that other providers of this same type of chips, of flux qubits, have. The first one is qubit quality. Some of other providers or of our competitors develop chips with many qubits, very big chips, like, I don't know, you heard D-Wave has 5,000 qubits, and that's an amazing technological achievement. It's incredible. They've been there for over 20 years, and it's really impressive. But they run with an issue that we think is very important to overcome, and is the lack of coherence. So they have coherence, but the coherence is very short, very, very short. The coherence, just I'm sure you all heard of this, but the coherence time is put in a very simple way, is the lifetime of the quantum information contained in a qubit. If the coherence time is very short, then the quantumness of your algorithm gets lost, and then quantum advantage cannot be harnessed anymore. If you don't have quantum phenomena at the end of your computation, then you lose all the quantum advantage that you could have. So in Qilimanjaro, what we believe is that first of all, before having very large devices, very large chips with many number of qubits, we want to make sure that we can have a single qubit that is very, very long in coherence, that it has a very, very good quality. So that's our priority. We put quality before the number of qubits that we can put together in a chip. And this is one of our main metrics. Coherence time is one of our main metrics. Then we have the other limitation that the technology is currently facing, and is the type of interactions. So you know that qubits can talk in different ways. So you can have XX interaction, you can have YY interaction, ZZ interaction, XX plus YY, XX plus YY plus ZZ. You can have many types of interactions. And this is allowing you having the ability to tune all these different types of interactions, allow you to construct arbitrary Hamiltonians. And as you saw before, having the ability to construct arbitrary Hamiltonians allows you to encode arbitrary problems. And this gives you the potential to have universal quantum computer in this paradigm as well. This means you can encode any Hamiltonian, quantum chemistry Hamiltonian, a physical Hamiltonian, something that you couldn't encode with the interactions that are nowadays being implemented. Also, we know that there are many theoretical proofs that show that the interactions present in the available quantum annealing devices only allow to encode problems that are called Kubo problems. I don't know if you heard of it, but basically those are problems that are being encoded in as a classical algorithm that solves them, mainly what is called Monte Carlo methods. Quantum Monte Carlo methods can solve these algorithms. Therefore, we believe that with this type of interaction, advantage. So this is another metric that we are also very keen on, is the ability to develop this type of couplings or interactions that are generally called non-stochastic. And it's been theoretically proven that with these non-stochastic couplings, having the ability of having this wider variety of interactions, we can solve problems that cannot be easily simulated with classical computers or with Monte Carlo methods, meaning that there's a potential to show quantum advantage if we have the ability of use these interactions. Okay, and the last limitation that we are also trying to solve, and we are also very focused on, is connectivity. Connectivity is a crucial feature, because in order to encode arbitrary problems, we need to have arbitrary connectivities in the chip. Usually the problem can be constructed as a graph. Usually the optimization problems are constructed as a graph, and the interactions are the edges of the graph. And these edges of the graph are the dependency between two variables, for instance. So if we want to be able to encode arbitrary problems, this means that we need to be able to construct arbitrary graphs, because every problem will have a different dependency, will be different. And if we have arbitrary graphs, then we need arbitrary connected qubits in the device. So ideally, we would like to have full connectivity. Full connectivity is when each qubit is connected to every other. But you can already imagine how dense this becomes in terms of the chip design and the fabrication challenges that this supposes when putting them in a planar to the chip. So usually the chips are planar, and if you want to have this full connectivity, this is very, very challenging. So the way other providers overcome this problem is by adding many ancillary qubits. Ancillary qubits are additional qubits that you put to mediate these interactions. However, this scales very badly. So the more qubits you have, the more ancillaries you need. And at the end of the day, this resembles very much to the issue that we have with error correction, that we needed a lot of redundancy. We needed a lot of physical qubits to encode the logical qubit. And so this is the same situation, but now instead of doing it because of the errors, you do it because you need the connectivity. So we think this is not practical. And in Qilimanjaro, we want to follow a different approach in order to avoid this overhead of number of qubits. And for this, we want to use software techniques that induce these connectivities as we need them. And it's not that much of a fabrication issue, but it's more of a control issue. And the last thing of our hardware solution is that we do not rely on third parties for fabrication, design, or operation, because everything is done fully in-house in our 2 Qilimanjaro labs. We have 2 labs at the moment in Barcelona. Okay, the next part of the solution is the software, the classical software. And this is something that we call the quantum as a service. This is the cloud access that I mentioned before. We want to provide to the users, and researchers, this cloud access to our quantum device, but also different backends. We also have classical backends that are basically simulators based on different approaches like tensor networks, or efficient GPU simulators and so on. And we want the user to be able to select the backend, have an algorithm, select the backend. Backend could be the quantum backend, could be the classical backend, and run their algorithms in a very transparent way. So they don't really need to care about the technology. They don't really need to know anything about that, because what they want is to run the algorithm, and we need to make it as abstract as possible, so they don't have to worry about the specific functioning of each of these backends. And okay, so for this, we have developed this software stack that contains a user-friendly interface that gives this remote access to our clients. And all of this is packed with a set of integrated quantum algorithms. This is what we call the Qilimanjaro portfolio, that are already designed to tackle some of the most common problems that we are aware of. And then the client can select one of these algorithms and tweak it or tune it according to their needs. Also, this software stack not only has the higher level of the application layer, not only has the remote access and the user-friendly interface and so on, but it also has all the necessary device control libraries. So this software stack also controls the real device, the quantum hardware, which is something that is very highly non-trivial. And it also has languages, intermediate language, and all the compilation methods that you need to go from the higher abstraction layer to the lower level of machine language. And all of this is also designed fully in-house to really tailor our needs and how our devices are integrated. Okay. Well, I must say that the development of this infrastructure of the high level and hardware agnostic level is being done through a programming framework that is called QIVO. I don't know if you heard of it. QIVO is something similar to QIQT. It's the same idea. It's a high level programming framework that allows you. The difference is that it allows you to program your algorithms not only for same type of machine, but also for many other different architectures. So it's very transparent to the hardware, as I said before. And we do this development in a collaboration. So this was initiated in Barcelona, but now this has become a very widespread collaboration. And mainly we do this with the Technology Innovation Institute of Abu Dhabi, but also QIQT. And finally, the last part of the full stack solution is, as I said before, the quantum algorithm portfolio. So this comes from our theory and applications team, which is the one I'm part of. And what we do is that we are equipped with the theory of quantum information and adiabatic quantum computing as well. And we have also very close collaborators from industry and other research centers, and with them all together we identify use cases. We focus a lot in logistics, finance, chemistry, but also more. And what we do is, based on this identification of use cases, we design the quantum algorithm solutions that are tailored both to the client needs, but also to the possibilities of the different quantum devices that we have. With this, we are constructing what I said before, this quantum algorithm portfolio that contains all the different quantum approaches that we identify and develop. On the other side, we are also having another major role in the company, and it's working with very close interaction with the hardware and the software teams. And what we do is to provide them theory support. So this includes helping them developing software techniques to improve the efficiency of any specific quantum algorithm, or the compilation methods, or the identification of proper languages. But we also help setting the requirements in terms of the architecture for the development of 4 different generations of quantum chips. So we help them. For instance, we can interact a lot with hardware teams, saying, okay, we need to have these interactions, we need to have this connectivity, we should do this way, and so on and so on. And finally, we also put a lot of effort, and in this sense, we really work a lot as an academic research group. We put a lot of effort in the research and development of the adiabatic model of quantum computation, and because we want to identify and implement all the ingredients that are missing in this model of quantum computation to make them truly universal, and to manage to also build this in hardware. If we manage to do this, we will make this approach a very viable competitor of the gate-based model, not only for the next decade, when it's not quite ready yet, but also for the long term, even when error corrector devices have already been developed. Okay, and finally, I want to present you the team. Now we have more people, so this is a bit of an old slide because we are growing very quickly, fortunately. But I wanted to explain a bit what is our working philosophy. I said before that we are a full stack company, and that's quite rare. That's not very common. But we believe that this is a good approach to efficiently develop the technology. And the reason is because we believe in what we call co-design development. And we are 3 different teams: theory, hardware, and software. And our interaction is based on this co-design approach, and for which we profit the full stack nature of our teams to constantly fit the chip design from the application requirements, as well as the software development, and vice versa. So we have a constant loop of interaction that allows us to improve not only the algorithms, but also the chip and the software interactions. And we go slowly adapting all the needs and requirements to what others have. So we work in a very well integrated way. And we hope that in this way, we can maximally harness the quantum advantage of our proposal to benefit the maximum the progress and also the client's needs. And with this, I'll finish, and I'm happy to answer any question that you might have. Thank you very much.
With this wonderful talk by Dr. Marta, I could see that she have gathered the thoughts, starting from how the idea of Qilimanjaro have started with their venture out, starting from academia to developing the industry and providing the solutions. She has spoken about the adiabatic quantum computing, and then the hardware platform that they have developed, and then the stack solutions, the quantum as a solution, QAS solutions that she have talked about, the software services for the quantum technology, and also the algorithms that you wish to develop in the platform. So really holistic approach to give the quantum technology and the computing platform with its advantage from the Qilimanjaro solution. So this certainly is an enlightening talk. I would thank you, Dr. Marta, for your talk on behalf of the organizing team. And also, we have a lot of questions, so I would see if, all are thanking you. So any questions specific to, okay, so there is one. How do we get such long coherence time?
It's based on I'm not a hardware person, but I'm going to try to answer this question. Is based on the circuit design. So when you have superconducting qubit, you have different circuit elements that you can put together in different ways. So you have different architectures. And depending on how you put this circuit together and the type of filters that you add and so on, you can enlarge your coherence times. So we focus a lot on, there are many ways of doing this, and we focus a lot on finding the different combinations of these elements and the different architectures to find this. But we do have a certain combination of the circuit elements that give us high coherence. So it's a matter of fabrication of the chip.
Any other question? Okay, while others typing, maybe I have something. On behalf of the students, I would ask, because like you see, like you started your discussion, there are so many students here, and ICER Kolkata is a spearheading institute in India, institute of national importance with a lot of researchers in this domain, spearheaded by Professor Panigrai and many other members. So there are a lot of students, interns who are working, and they have also their passions towards applications. How do they apply their knowledge to the product development, so that they can see that technology is growing and they are contributing. So from the industry side, I mean, what are your expectations from the students? I mean, what some things that you would like to give advice to them that they should focus, and also how your organization could further collaborate with such academics, and what kind of offerings do you have for your students? For these
yeah,
students?
I actually didn't comment on that, and maybe that was a useful thing to say, given that there are so many students. So we work very close with research groups. As I said before, for instance, my team works very much as an academic group. We make publications, we go to conferences, and we have collaboration seminars and so on. And one thing important that I didn't mention is that we have something that is called industrial PhDs. So industrial PhDs are a collaboration between university and companies, research and development companies, that what allows the student is to do the PhD while they are in the company, while they are working in the company. So the company pays the student, and in the meantime, the student works for the company, but works towards having a PhD thesis. So this can be done if you have a research line in your company, but it is something that in Qilimanjaro we are doing. We're focusing a lot because we think, as I said before, one big issue that we encounter is that there's not that many people that want to work on this and has the expertise and knows the theory or the experiment, especially the experiment. It's very difficult to find people with knowledge in the hardware side. So our solution was to have these kind of programs to grow with the students. So we try to form them, and then we also try to give them continuity in the company. So after the PhD, we offer them a permanent position to keep working with us. The other thing that we did is that we co-created a master in quantum technologies in Barcelona, the University of Barcelona, with two of the founders of Qilimanjaro helped doing that. And this master program has run for the first year, and we got final master project also working in Qilimanjaro, and we are also going to give them continuity because during this master's program they also learned a lot of the skills that are needed to work in a quantum tech company. We also offer internships. We also have paid internships for the summer and also during the whole year. So if anybody is interested, you can write on the we have a website, and you can send the CV there. And also we are going to grow in the future, so that will mean that we will have more opportunities. But an advice for me when when I started in the field, I come from chemistry and computer science, and I really wanted to be in quantum computing. So for me, it was quite a journey of trying to get there. And I encourage students to don't be afraid of jumping to different fields and do a postdoc, do an internship, and you can go back and forth from industry to academia, and you will learn different skill set, but that will always be very useful for the other way around. So in academia, you will learn a lot of skills that will be very useful in industry. And I think in industry, you will also learn a lot of skills that will be very useful if you want to continue your research in academia. So I encourage students to try different ways. And I think it's a good moment, very good moment for the field. And there are many opportunities out there.
Great. So I think that also answers the next question, that you have internship opportunities. You have also industry-sponsored PhDs. So talk to your faculties in ISER. Develop some research work so that you have some hands-on experience, so that you could, like Sisi mentioned, a lot of gap in quantum hardware, especially in the hardware side also. So do develop that, and then work with the research team of your institute to develop some research proposals, and then to them. There is another question that I'm back to the question. Do you use feedback control to stabilize your qubits, or they are put in cryogenic baths?
Yeah, we have cryogenic refrigerators, and I didn't show the picture, but we have a very novel one. I'm very proud of this. We have you've seen the typical Blue Force big refrigerators that they have. IBM has, Google have. They are very big. But now we just got in our hands a smaller fridge. This comes from a startup in Europe that we call it a tabletop quantum computer, because it doesn't have to be suspended from the ceiling anymore. It's done more efficiently, and the size is reduced. And in principle, you don't lose capabilities of refrigeration, and you can put it in a table. So it's still quite bulky, it's still quite big, but it's much smaller because it's been developed more efficiently, mainly focused for quantum computing. And in a limited amount of space, you can fit the same amount of qubits, more or less, and all the control fit lines. And yeah, I will include another picture of this in the presentation, because it's something very, very uncommon to see in these very smaller size fridges. But that means that it's more efficient in terms of consumption, because as you know, it needs a lot of helium and other gases, and helium-3 is quite expensive. The liter of helium-3 is really expensive. So by having a smaller one, we can optimize the cost, and also the energy consumption and everything.
Any other questions? If you need to ask some questions, you may also speak up and ask your questions. Or any more questions? Okay. Okay, if no more questions, then I think let us thank Dr. Marta once again for this wonderful discussion and about the new technologies that Qilimanjaro is developing, and also their path in collaborating with academia and other industries to develop these solutions, which is our future of the computations in the years to come. So with that, I would thank her once again, and
thank you very much for the invitation.
Conclude this session. So thank you.
Thank you very much.